Hello and welcome to the MecSoft demonstration series, where you can see live demonstrations for real users and real-world applications. For more information about our products or to schedule your own live demonstration, just give us a call or visit us at www.mecsoft.com. Without further delay, we invite you to sit back and enjoy the demonstration.
Now, the first step I'm going to do here is load our library of tools. So by going into Load Library, and I believe I have it saved over here, I just call it My Tools. I'm going to pick Open, and that loads the tool library right into RhinoCAM. So it has 10 tools defined. I can go ahead and add the additional tools for the bevel tool, the chamfer, and also the carbide ball nose, and also the chamfer tool. So if you want to add a new tool in here, you can go back and edit a tool, and I can basically call this a 50mm bevel tool, and I can put in the tool diameter and specify the properties for the tool right in here and set this and then save as a new tool. Now I can add a 10mm ball nose cutter. Now I can also set the feeds and speeds for the tool in here. If I need to make a change, I can click on Edit Tool and specify the properties in here, where I can specify the spindle RPM, and I can specify the feed rate to be 200 millimeters per minute and save it as to tool, so the tool properties are updated. Now for the ball mill, I'm going to define this as a 10mm carbide ball nose, specify the properties for the tool, and then the feeds and speeds you have 2000 and 500, so I'm going to specify 2000 and use 500. Now we also have a built-in feeds and speeds calculator in here, and this can help you determine feeds and speeds based on the surface speed, the feed per tooth, the properties of the tool. Since you have certain predefined values, I'm just going to go with that. And then finally we have a 10mm chamfer tool. We'll go back and add that as a chamfer tool right in here. So if the chamfer tool is converging to a tip, then you would define it under tool type called V-mill, or you can define it as a chamfer tool which has a flat diameter, or even you could do a taper ball mill if it has a radius, corner radius to it. So in this case, I'm going to just define it as a 10mm chamfer tool and specify the diameter right in here, and I can set the tool length, shoulder length. I'll also specify the feeds and speeds in here, use 6000 and 1100, and save this up as a new tool. So the tools are numbered from 10 all the way to 21.
Right.
Now, once I have these tools defined, I can just go back in here and save them back to my library. I can update the tools to the library. So now I have total of 13 tools being saved to the library. Any questions about creating your tools and saving them to a library?
No, that's pretty straightforward.
Okay, great. Now RhinoCAM allows you to define different tool types: ball and mills, flat and mills, corner radius, tools for engraving or chamfering. You also have taper tools, thread mill, face mill, dovetail, corner rounding tool, or called fillet mill tools. You can also create lollipop cutters, and form tools or user-defined tools, so you can actually create or draw the 2D cross-sectional profile of this tool in Rhino, where the tip being at the origin, you can model a tool, and then once you pre-select it and then click load selected tool profile, this will revolve it to define a tool as well. So you can have form tools defined.
Okay.
Alright, so we have all of these tools defined in here. Now the next step we would like to do is go ahead and program some toolpaths. So in the mill module, you would want to go to the program tab and you define your machine tool definition, whether you're going to be using 2 or 3 axis or 4 and 5 axis operations, depending on type of operation that you're programming. You pick the number of axes. For 2 and 3, you would select 3 axis. And if the machine that you have has an automatic tool changer, you can leave these numbers as zeros. If you are working off a manual tool change and you'd like the tool to be moved to a specific XYZ origin location, based off your origin location, you can specify the coordinate value, and in the post we can set it to output this information as well.
Okay.
Alright, now the next step is to establish the orientation from which you're going to be machining this part. So you can go under setup and change the orientation if needed. Now since this part is round or circular, you currently have it set to the center, and so we don't need to flip the X or the Y orientation. So you already have it defined and designed where you need it to be, so you can skip the step of orienting, and we can now go ahead and define the stock or the workpiece. You can go to stock. We could start with the box rectangular stock or a cylinder stock, or you could even do stock by extrusion, stock by selection as well, which are offered in our Pro configurations. With our standard, you could do box and cylinder stocks as well. Now, are you going to be starting with a rectangular piece of blank, or would it be a round blank?
A square.
A square. So you would pick box stock in here, and the moment you select copy model bounding box, this will determine the minimum size of stock material, the workpiece that you need, and you can enter in your length, width, and the height. So if you need to change this to, let's say, 275 or 300 millimeters, you can enter in this information in here so that your stock is starting with much larger than the actual part.
Mm-hmm.
Now, would you have a recommendation on what you would like to start with?
No, because it can say 280 mil square.
Okay. All right, so we'll do a 280 mil, and then height would be 6 millimeters. Is that right?
Correct.
Okay, we'll accept that. So the stock is now defined right in here. Now we need to align the stock to the part, so we go into align and pick align stock, and now I'm going to have it centered in X and Y. So the stock is now positioned right in the center. Now by default, the machining coordinate system origin is coincident with the world origin in Rhinoceros. So your XYZ origin, or your work 0, or you call it your G54, your work offset, is coincident with the world origin in Rhino. If you need to change the location of the origin, there's a couple of ways we could do it. One of the ways is we can actually move the part and the stock to a desired location, like a corner position, or you could add what is called a work 0, and you can transform the location of the origin to any corner or even any point of your choice. And this can be output as your G54, 55, 56, or whatever the work offset number is.
Okay.
And now you pick generate, and your work 0 is now translated from the machining origin. So you'll notice that the XYZ0 for the workpiece is being set to the top and the southwest corner, whereas the origin in your CAD still remains at the center of the part.
Right.
Now if you'd like to set it back to the center of the part, you can double click to edit the work 0, and you can pick set to stock, high as Z, center. That'll basically place the origin back right where it is. And you can also change these values in here. You can go pick and then put it right at the origin by specifying 000. Okay, any questions so far, Robert?
No, that's right.
Okay. Now, how do you typically plan to program this in here? You want to probably do a profile cut around these areas on the outside, and you need to cut these pockets out, right?
Yeah, that's correct.
And on the inside, do you plan to just do like a profile cut, or do you need to do a pocket too?
One profile cut.
Okay, so let's start with the inside profile cut in here. So we'll go into our machining operation. So we go to 2-axis, and we have a wide range of methods in 2-axis. We have starting with roughing, facing, pocketing, profiling, V-carve roughing, V-carving, engraving, slot machining, chamfering, hole pocketing, hole profiling, thread milling, and T-slot machining. Now these are offered in configurations starting with standard. Now in our Pro and Premium configurations, we also offer remachining, which is like rest machining. So if you profiled it or pocketed with a larger diameter tool, you could go back and machine with a smaller tool, so it knows the material that's being left from the previous step.
Mm-hmm.
So let's start with the profile operation. We'll pick profiling. Now you can click on select curve edge region. So this basically displays your profile operation dialog. And as you select curve edge regions, you can select a curve, which could be a closed curve or an open curve that you have in Rhino, or you can even pick a set of open curves as and chain them together, or you can even select the surface edge from the model. Since I've changed it already, I just had to make one selection pick, and then right click or press enter accepts my selection.
Mm-hmm.
Now the next step is to make a selection for the tool. And would you like to go with the 8mm rougher?
Yeah.
Okay, so I'm going to select this. Tool number is set to 13, as you can see right here. If you need to modify it, you can always select edit, and you can modify the properties of your tool as well. And then what we have next is the feeds and speeds. I have it set to load from tool. you had a feed rate of 350 millimeters per minute set for the cut feed, so we automatically set the plunge approach to be 50 and 75%, and then the retract and departure is 125 and 150%. But if you need to change these parameters, you could always do so. And then you can also set your feed rate for rapid, so this will be used for a G0, or if you pick set, it'll do a G01 for transfer feed rates. Now the clearance, by default it's set to automatic, so it'll use a safe height for clearing your stock and the part material for the transfer motions. The next step is to specify your cutting parameters. You can set your tolerances for the profile operation. You can specify stock to leave. If you want to use the profile as a roughing pass where you want to leave some side stock or a wall stock in here, you can specify to leave some stock. Would you like to specify a stock to be left on the roughing operation?
Yeah. We'll say
And
0.2.
0.2 millimeters. Okay. You can choose your cut direction, climb, conventional, or mixed. Would you typically use climb cutting?
Mm-hmm.
Okay. And then you can choose what side to place the cutter, outside or inside. I choose inside.
Yeah.
Now in this particular case, since I've extruded it to be a solid model, I could also select to determine using 3D model. So RhinoCAM will determine that the cut needs to go on the inside and not on the outside of this curve.
Right. Okay.
So you can use this option in here. And in the cut levels, you can specify your depth, and you can pick the depth of the model. So we know the depth is 6 millimeters, but if I was unsure, I can use the top edge, select a point near the bottom edge, and it establishes the total depth of 6 millimeters. And would you like to program the 6 millimeter in multiple Z levels?
No.
Just one cut?
Yeah.
Okay, perfect.
Can you
Then-
increase it more than 6 millimeters?
Absolutely. You can specify in your value. I can say I want to go slightly into my wasteboard or spoil board. I could say I want to go like 6.2 millimeters, for example.
Yeah. Yeah.
I can put that in here. I can establish these parameters. And in the entry and exit, I can choose the type of entry and exit. I could do lines and arcs. I could do a long path, or just do a plunge. So I would suppose you would either want to do a lines and arc or a long path in here. And you can specify the approach, engage, retract, and departure motions. So you could do keep it tangent. You can do linear or arcs. I can specify a value for it. I could put in 3 millimeter radius for each of these. And finally, since I've tightened up the fitting tolerance for the global cut tolerance, I'm going to set my arc fitting tolerance to be 2 times for that, and then select generate. So in this process, you'll notice that it creates a profile cut, and it starts right in here. Now, by default, it is set to use the midpoint of the longest edge. If I clear this checkbox, it'll use where the start point of the curve is set in Rhino. So in this particular step, the start point is over here on the right side at the 3 o'clock position. When I generate it, it'll apply the entry and exit right over here. You can also set an overlap distance in your entry and exit so the cutter goes past on your lead in and lead out.
Right.
And you can always change these parameters in here. If you need to make the lead in and lead out much larger than what it is, you could always go back and change these parameters. You could also use a linear as opposed to a radial entry. So all of these parameters can be set, and there's your linear entry.
Mm-hmm.
There be any questions so far?
Yeah, I do have one question. With the profile that you've got there, if during the construction phase with CAD, you were to do that in mixed sections, like say you did a bit over on the left and a bit over on the right, does the profile have to be chained so that they all follow in, like each element follows in order? So
We could do what is called a sorting, and we can specify a sequence for the sort. So we don't really have to have it chained, but you can specify it to sort them, so go from one pocket area to the next area.
Mm-hmm.
Or you can automatically have it do based on the order in which you select them. If you don't want it to sort it, you can pick the sequence in which you want it to cut.
Mm-hmm.
So I'm going to make a new layer in here. I'll just grab this curve. I'll place this on the layer. I'm going to say copy object to this layer. Okay, and let me use this curve that we have right in here, and I'm going to explode this in Rhino.
Mm-hmm.
And we may just want to pick certain sets of these curves in here, right? So I'm going to select these curves. I'll join them together. And I'll retain, so we have this curve right in here. Now is this a good section to take a look at?
Yeah.
Okay, and then I'm going to do the same thing over here and not have these selected right in here. So I'm going to join those. So basically I'm joining them to one curve in Rhino. So just to make our selections easier, so what we are trying to take a look at here, right? So I'm going to drag a window to select them, just drop these to radius, join them together, and do the same step in here. Select these, drop these to fillets, join them, and repeat the same. Now I could have also used the Rhino tools where I could have done an array of these, polar array, rather than having to go through each of them. Now on the profile operation, I'm going to go ahead and remove these and then use a selection. I could use an order to select them. Okay, and then I can choose which side to place the cutter, to the right side or to the left side. If you take a look at this start point in here, if I pick cut to the right, the cutter is going to stay on the right side of this curve as it follows along. But we would like to maintain it over here on the left side. So in the cutting parameters, since this is an open curve, I'm going to pick right or left and then choose generate. So you'll now notice that it's using the cut direction, what you specified. Use cut right or left. And the lead in and lead outs, which we call it entry and exits, are automatically applied. And since I chose them in a specific order, it's using the order in which I selected. Or if you go to sorting, you can use a minimum distance sort, and that'll change the order in which it's starting. So there's the profile cut. Would that help?
Yeah. That's good.
So you can either do the entire chain like we did over here on this particular step, or you could break them up into different sections. So this is the simulation of the profile cut for the entire chain, as you notice it. Okay?
Yep.
Alright. So we got the profile programmed in here. The next step is to program these profile, or would you like to do them as pockets on these areas?
Pockets.
Pockets, alright. So would you like to use the same cutter?
Yeah.
Okay. So we'll do a 2-axis. We'll pick pocketing. And now I'm going to drop these areas and then just select these curve boundaries in here. So I can select a curve, or I could be selecting the surface edges from the edge of the 3D model. Now the 3D model representation helps you determine the depth and helps you, take measurements of the parts. It makes it a lot easier, and we can also use feature detection and machining when we work off a 3D model. So we'll use the same cutter, is that right? The 8 millimeter pin mill? Okay. In the cutting parameters, I'm going to set the tolerance. Would you like to leave like a side stock of 0.2 millimeter?
Yeah.
Okay, and then you have different cut patterns in here. You could use offset pattern, offset spiral, linear, spiral, radial. We even have a high-speed cut pattern, which is like your troical cut pattern.
Okay.
You can specify your cut direction, your step over. In the cut levels, you can specify the depth. So we would like to go 6.2 millimeters. And would you like to do it in one cut? You can specify that, or if you want to break it up into multiple passes, you can do it right in here. You can also set your entry and exit for pocketing. You can ramp along the path. You can specify the path ramp height in here. And you can specify the retract parameters. In the advanced cut, you can set your arc fitting tolerances, and generate will create your pocket toolpath. So this is the offset cut pattern where it creates a uniform offset of the curve geometry.
Right. And it's got a spiral leading.
Yeah, it's doing a helical ramp, a path ramp right there. Now I'm going to go to the Simulate tab and select Play to run the verification. And we are still leaving the 0.2 millimeter stock from the sides of the pocket. And you can always change the simulation speed to have it go faster or slower as you wish. You can always do pause and simulate to end to run through the simulation. Now the next step I would like to do is go back and profile these, right? Profile finish these features. So I'm going to make a copy of one of these operations, right click, select copy, right click and paste, and now I'm modifying it and selecting these features for profiling. Now in this particular step, you'd want to go from a roughing tool to a finishing tool, is that right?
Correct.
Okay, and then you got your feeds and speeds set, your clearance is set. In the cut parameters, you would want to go on the inside, leave 0 stock, specify your cutting parameters in here, and you can use the midpoint of the longest edge for entry and exit. Now all of these parameters are set, and all you got to do is generate. So that gets you a profile finish toolpath, and it's using the same entry and exit settings that you had set. So copying and pasting an operation copies all of the parameters into it. And if you need to use a cutter compensation like a G41 or a 42, we could enable the cutter comp to be toggled on, and then the compensation can be done at the control.
So look, can you actually generate the code with the cutter compensation taken into consideration?
So when you use cutter compensation in here, we have auto on, so which means when you select auto on, the toolpath is still being compensated by the tool that you defined in here, which is it's automatically compensated. So what you're compensating on the control is more like a tool wear. So if the cutter is worn out and it's 7.8 millimeters as opposed to 8 millimeters, right?
Yeah.
You'd be compensating for the 0.2 millimeter. Now, if you need to program it on the geometry itself, like a centerline cut, the way you would have to do it is in the cut parameters, you have stock to leave, and you would need to specify this value equal to your tool radius. In this case, that would be -4 millimeters. So when you generate it, it'll actually put the tool path back on the geometry. However, this is going to invalidate the simulation, but then you would be compensating for the full diameter of the cutter at the machine.
Right.
So,
so you can't simulate it and generate the... See, probably way to... Well, the way I taught was taught to program is to program the part, not the tool. So I could take later on, if I wanted to do that pocket with it, finish that pocket with a 10 mil cutter, all I have to do is update the controller's D value to 5 mil, to sort of 10 mil cutter instead of 4 mil for an 8 mil cutter.
Right. So in this particular step, what we did was we put in a stock value of -4 millimeters since the cutter we used was 8 millimeters. So this basically clears the offset and puts it back right on the geometry that you're profiling. So this is how you would basically compensate for the full width of the cutter. By doing this, it's going to invalidate the simulation because the simulation would show it's going to be cutting on this particular geometry.
Yes.
So if you need to do that, then that's how you would have to do it, by specifying the stock value in here. If you set the stock to 0, then it's automatically compensating, and this would not invalidate your simulation.
Right.
Okay?
So RhinoCAM can't simulate that the tool is offset, but generate the code as if it's not.
Well, if you need to make sure both of them look correct, then this is how you would do it. And then when you post it, we do output a G41 or a 42 with the D value, but then the toolpath is auto-compensated.
Right. Okay. So the answer is no, it can't simulate the tool being offset.
The tool being on the geometry. Yeah, that is correct. It'll invalidate the simulation. It will simulate it, but the simulation results would be invalidated as you're pushing the tool back on the geometry, so it would show that it's been cutting the pocket larger.
Yes, correct. All right. And I take it that's the same scenario for the internal profile as well.
Absolutely.
Okay.
Okay?
Mm-hmm.
All right, so now let's go ahead and finish off the internal profile in here. So I'm going to repeat this operation, do a copy, and we'll paste it down here. And we'll make sure we select the finishing tool for this as well. And we'll specify not to leave any side stock and generate it. So this basically finishes the internal profile. Now we also have an option in here to remove remnants during simulation. So that'll basically show you what's being left or what's not being left, so you can choose that. So in this particular case it's retaining the outermost, but what you really need is to retain these. So you have multiple layers of pockets, then the remove remnants is not going to be applicable in this particular scenario.
Mm-hmm.
Okay, now the next thing you'd want to do is program these holes and then do the profiles. Before you do the profile, you'd want to do the chamfers on these edges. Is that correct?
Correct.
All right. Now the holes in here, let's check the size for these holes. Analyze diameter. So those are 8.5 millimeter.
Mm-hmm.
So I suppose you'd want to do a spot drill and then a drill for these holes.
Yes.
So we would start with a hole machining and drilling operation. You can select your drill points. You can graphically select them, or you can even drag a window to select all the holes by diameter or on a layer. You can select those. So once you have this selected, you could go ahead and specify your tool for it. So would you want to use the CNC stub drill for it?
Yeah.
Okay, I got your feeds and speeds set from the tool, loading it from the tool. Specify your clearance. In the cutting parameters, you could specify the total depth. So on the spot drill, you would want to specify how deep you want it to cut, like a 0.5 millimeter or 1 millimeter.
As in peck drilling.
Okay, so you want to do a peck drill, then we could do a deep drill. But if you just want to kind of just go ahead and mark the holes first as a reference,
Right.
like you can do just a spot drill or just to mark it. You could do that, or you could go directly to a drill operation. Again, if you want to do a peck drill, we pick deep drill. We specify the total depth is 6 millimeters or 6.2, and then you can also add the tool tip to drill depth, so we'll automatically compensate for the tip angle of the tool to do that. And then you can specify your step increment. This is where you specify that you want to go in 0.5 millimeter, 1 millimeter, or whatever is the peck increment for it.
Sure.
So I'm going to put in 2 millimeters for the peck increment and then generate. So this creates your drill operation. And now we're going to go to the Simulate tab and select the drill simulation. You can see the peck motions being simulated.
Mm-hmm.
Okay. So we got the drill operation done. The next time is do you want to do the countersunk on these?
Yes.
Okay, so hole machining, drilling, and you already have these set in here. All I'm going to do here is go from standard drill to countersunk, and I would pick the countersunk tool in here. And is the countersunk diameter going to be 25 millimeters?
Yes.
Is that the diameter of the countersunk hole, or do you know?
I don't have that information.
Okay, we can determine this right in here. Analyze diameter, and that would be 16 millimeters.
Okay.
So I'm going to put in the countersunk diameter to be 16, and the system will automatically determine that depth for us, so I don't have to go ahead and do the math for the countersunk. And there's the countersunk operation.
Yeah. So can I just ask a question there?
Mm-hmm.
With regards to the holes and the countersinking, can I, in Rhino, can I assign a tool to do those things without actually having to generate the toolpath?
You would have to generate a toolpath by either having a point or a circle to define your geometry, but you don't have to model it as a circle.
No. Yeah, I understand that, but as you would draw that in Rhino 3D, you draw it as a chamfer. So is there any way of assigning that tool that you just picked to do it to that chamfer so that it automatically recognizes that that tool needs to do that part of the job?
Yeah, you could.
Such as the same with the drill for the holes.
So what you would do is we have what is called a knowledge base, so you can basically have these two tied into a knowledge base. So when you have family of parts or parts that are similar, you just load the knowledge base. It'll have the tool and all the parameters linked to it. The only additional thing you got to do is just select the geometry that you want to use, or you could even automate that by establishing selection rules. You could have it set to select geometries by a certain color or certain layer, so you can automate your workflow.
Right, okay. So I could put the holes on a different layer and assign that drill to that layer.
Absolutely.
Right, okay.
So now I could take these geometries that are currently pre-selected in here, and I can create a layer called holes drill, and I'm going to change the object to this layer. And I'm also going to go ahead and select these holes in here. I'm going to select these larger holes. I'll make a new layer called countersink. I'm going to change the object to this layer. So now I have these holes on different layers in here, right? I've organized them or structured them in layers. And I'm now going to go ahead and save these to a knowledge base. And I'm going to save it under the data folder. I have this saved to a knowledge base. And I will also go ahead and select all of these drawings in here. I'll export this out to a separate file in here. Call it test part 2. Okay. Now I'm going to go into knowledge bases and establish some rules in here. And I'm going to establish just for the drilling operations. I'm just going to go ahead and clear these out, but the workflow will be very similar. So for the deep drill, I can have it select automatically all objects on layer called drill. And for the countersink, I can select a rule to select all objects on layer countersink.
Mm-hmm.
And then I'm going to save these back to a knowledge base. Now I'm going to go ahead and load the drawing we were working on. So I'm going to open up another file in Rhinoceros. So it's loading Rhinoceros. I'll go ahead and load this part, which is called test part number 2. And as you can see, we do not have any operations in here, but we have these objects in different layers. So I'm going to go ahead and load my knowledge base, the one I just created. And all I do is right click and generate. You can see that the drill and the countersink are automatically generated with the rule set, so geometries are automatically selected, and you can see that the tools are being selected based off the knowledge base that you've established.
Okay.
So that's how easy it is to automate the workflow.
Mm-hmm.
Okay, so I'm going back to this part right in here. So we got the countersink and we have the deep drill taken care of. The next step is to do the chamfers on these pockets, right?
Sure.
So you would want to use a 2-axis and use chamfer operation, and you can select these features in here from the viewport directly. And this chamfer is about 2.5 millimeter, is that correct? The width of the chamfer?
Yeah.
Okay, so you go ahead and select a tool for chamfering. So you have the 21 millimeter or 10 millimeter. Would you have a preference on which one of these tools you'd like?
10.
10. Okay. and then got the feeds and speed set. It's being loaded from the tool. Your clearance is set. In the cutting parameters, all you got to do is you establish your tolerances. You put in the chamfer width in here, which is 2.5 millimeter. And if you'd like to do a tip clearance so that the tip stays right off the edge, so you can specify a tip clearance, I could put in 0.5 millimeter, and then you can do a maximum depth per cut. And I'm going to just do it in one pass, so that'll be 3 millimeters. You can choose your cut direction, cut side, and you can specify entry and exit in here as well. So I can specify how I would like the cutter to lead in and lead out on it. And of course you can always do the fitting of arcs to your tool paths, and you can sort them by a minimum distance. That basically creates a chamfer operation. And if you need to make any changes to any of these parameters, you could always double click on it and make edits to these parameters right in here.
Okay. Can you select where you want the chamfer to start?
Absolutely. For profiling and chamfer operations, we look at what is called the start point of this curved geometry. So I can select this, and in Rhino I can go to the curve tools. There's a tab right here. You can change the start point. So I can pick the start point. I can say I want to move it to the midpoint right here.
Okay.
So I can pick a close curve. So now when you make a change, you just have to regenerate it, and you'll notice that the start point is getting changed. So select it, do a curve seam command in Rhino, and that'll allow you to drag the start point over. So you can just have to repeat it for each one of those geometries. Or you can do it on one, and you can array them over. So pick the curve, right click will repeat the last command that you used, and we change the start point on each of these. And the last one right here. So now I've changed the start point on each of them. Right click and regenerate will update the toolpaths. Now let's go to the simulation and run a verification on it. So by putting in the chamfer width, the depth is automatically determined by RhinoCAM.
Okay.
In this case, it's happened to be a 45-degree chamfer tool, so the width, the depth equals the width that you put in.
Sure.
Now you want to repeat the chamfer for these curves in here as well. So this process would be the same. I could do a copy and a paste. Edit the operation. Now do you want me to select the entire chain or just the fraction?
The entire chain.
Entire chain, okay, we'll accept that. You have the tool selected, and you just need to specify what is the chamfer width for those inside.
Just make it 1 mil.
1 millimeter, okay. And we'll do a tip clearance of 0.5 mil, and then generate. So that'll give us a inside chamfer. So you really don't have to model it in a 3D model, just right off of a 2D curve. Now the chamfers are programmed for the inside as well. Now the next step you want to do is go ahead and do the outside cut. So that would be a profile cut. So I can use one of these operations that we had. We'll select the profile operation in here, make a copy, and then paste it down here at the end. And we'll double click to modify it. Select this profile. And you'd want to specify what size cutter you'd want to use for it. Would you still want to go with the roughing cutter?
Yeah, right, rough.
Okay. And then would you still want to leave a 0.2 millimeter stock around it?
Yes.
Okay, and then we want to cut on the outside. And we can specify if you'd like to do it in multiple levels. You can use depth per cut. Your entry and exit can be set. Workflow is very similar to what we did earlier, and we have a profile cut on the outside. And if you need to change the way the entry and exit occurs, we can always go ahead and modify these parameters in here. You can also change the overlap distance. And there's the location of entry and exit. Now if you want to change it to be more normal or 90, you can change those values in here. You can put in like 0 or maybe 1 degree. So you can change these parameters for entry and exit.
Right.
Okay?
Yeah.
And I can also change this to be normal too on the entry, similar to how you had it set up earlier. Do you see that, sir? Okay, and now we go ahead and run a verification in here. So it follows along the profile. As you program it. And then you can repeat the same operation over again to run a finish pass. And these parameters can be changed, the length, and I just left it at 3 millimeters. If you want to increase the length, you can always do that. So run a finish pass and make a copy, paste, modify the operation, change the stock to 0, generate. So that will give us a finish pass to go ahead and clean up the material being left. Would you have any additional questions, Robert?
No, at this stage, no.
Okay.
The only thing is that I like to add a lot of comments to my programs.
Okay.
Between each, obviously it's going to select a few tools there, so giving the tools names, descriptions of the tool.
Now those
comments.
things can be automatically handled in the post processor, so there's a couple of things you could do to improve it as well. As we can automatically output the tool name as comments. We can also type in any comments that in addition to the tool information that you already have in here to be output in here. You can put that in there and we can output that as well. Like for example, to the operator, you can say, what is the specific tool that you want to use, like, the manufacturer of the tool or where you source your tools from. You can put in any additional instructions in here. Also on each operation you can go to properties and specify a certain comments to output.
Okay.
Now what machine controller do you typically work with, so we can go ahead and post process these out to your machine and show you that.
It's a panic.
Okay, so we'll do a post and we can select the post processor here. So we currently have over 225 plus different posts in the library of posts that are included, and you can select the post from the list. You said it's a FANUC OM?
OIMC, yeah.
Okay, so we should have one on the list here, OIMC. We have one for the lead well, but we can modify it to, change it to your machine, and then you specify the folder, and I'm going to put it on my desktop. I hit post. So as you notice here, it's automatically outputting the name of the operation in here, the tool information, and it's outputting in metric units, millimeters. So we can also output the list of the tools right at the beginning. We can also add any additional comments that you'd like to output. We can modify the post processor. It's very easy to edit the post, and I can go ahead and save this as a new name in here. I can select this lead well. I can change this to something else. I can call it just revision 1. And now I can go ahead and also add additional information, like you want to output the tool list at the start, we can do that. If you also want to output a tool name in here, we can output the tool name as a comment before the tool is being selected or after the tool is selected. So we have variables and macros in the post that can allow us to do that. So I can grab the tool name variable and I can put it in here. So there's a variable for tool name. We can also output any additional information with the tool as well.
So in your comment section in your tool folder, that will output that section there. Whatever you put in there will come out at the beginning before it generates the code.
Well, it'll be at the beginning of that when the tool gets selected. Now, if you want to output the entire tool list, I'm going to show you how to do that in here. So we can output all of the tools that are used in the program. We just have to set up what is called, we have an environment variable that we set up, and once we set that up, it'll automatically write the entire list of the tools in the output file, and I'm going to show that to you here in just a moment.
Mm-hmm.
So it'll output all of your tool information into at the beginning of the G code in here, and I'm going to do that right now in just a moment.
Mm-hmm.
So we typically do that by setting up what is called an environment variable, and that'll automatically, it's an optional thing that you can do, and it'll output the tool list. So let me go ahead and show you how to do that in here. Now while I'm working on that, did you have any other questions?
Not at this stage.
Okay. So we have an option where we can output the information about the tooling in here. And I'm setting it up right now, so I'll be able to show it to you in just a moment. Okay, so when I post it out, I'll rewrite the same file. You'll see that it outputs the entire tool description at the beginning of your program.
Right.
So we set up an environment variable on the computer that you have the CAM product installed, and then it'll output all of the information. It has the tool number, tool name, all of the description.
Sure. See down just under where it says 2.5 axis profiling there. The next line is tool 13 MO6. Is it possible to set the post processor up so that it prepares the next tool that it's going to use under that line of code there?
Absolutely. So here's what we're going to do. Go ahead and use this modified post, and I'm going to go over here, and I'm going to use a variable to output the next tool number. So we should have a variable called next tool num.
Mm-hmm.
I'm going to place this right in here,
Mm-hmm.
and also I'm going to add this for every tool change as well. So you want to preload the next tool so the machine is aware of it, so you can prepare it.
Yes.
So now you can see that the T13 MO6 shows up right there. That's your first tool, and then it's loading up the next, preparing the next tool.
Very good.
So your post can be customized, and also if you go to the next tool change, you'll see the T16 and then followed by T10.
Mm-hmm. Right. Okay. And of course, you can turn your line numbers on or off.
Absolutely. So that's again a setting in the post processor. We could toggle off the sequence number off, so that'll stop it from outputting the line numbers. And now when I repost this code, there won't be any line numbers. So there's a lot of nice features that you can modify and customize in the post processor.
Right. So are you actually which version of milling are you demonstrating today?
So whatever we did here on these these operations there can be programmed right from our standard configuration of the product.
Uh-huh. Okay. Are you able to demonstrate what the capabilities of that standard module is for doing 3D machining?
Can you repeat that again, sir?
Are you able to demonstrate like some of the features of that standard package for doing 3D machining?
Sure, absolutely. So you would like to take a look at some of the 3-axis machining capabilities? I'll be more than happy to do that. Now, in 2-axis, there are more methods. You can always refer to the what's new video that's on our YouTube channel to get more information on it. Now we can also use feature detection and machining that's actually available in our 2017 version. So there's a features tab right in here, and if you have a solid model built in, you can detect features by selecting just the face on the part, and it can detect features for you. So once you select the face, it'll identify the features, like it'll identify pockets and profiles, and you can program those. Now I'm also going to go ahead and show you that it identified these features right in here, as you can see it, right? The whole features, you can identify it. Now let's go ahead and take a look at some of the other type of features that can be identified in RhinoCAM. And also let's look at some of the 3-axis operations as well.